with this type of problem, they are giving you your least squares regression line and the equation for it, which in this case has a transformed data set. So you're looking at the natural log of y hat. And let's look at this now. So if we are looking at the closest to the predicted carbon dioxide emissions, and x represents the fuel efficiency, y hat represents the predicted carbon dioxide emissions, and they tell us that our fuel efficiency is 20 miles per gallon. Basically, this 20 gets substituted in for x. You might have to read that to parse through and figure it out, but that's what we got. So I have the natural log of y hat equals 7 minus 0.45 times 20. Now the right side can be evaluated pretty quickly, and that will be 6.1. Now that would be the answer if it was just y hat equals that, but it's the natural log of y hat. So what we have to do, those of you who answered B, you did all but the last step, which is, yep, that will happen. So just be on the lookout for that. We need to raise both of these to the e to the power of, and so on and so forth, and you will get 445.9, something like that. So basically 446 is your correct answer, not 6.1. Yeah, it really was. Difficult, lemon difficult. So today we're going to continue with linear regression. We're going to look at the t-test, but before we jump into that, don't worry about that previous slide. We are going to continue with what we left off with yesterday when the bell rang. So as a reminder, your stat plus or minus the critical value times the standard error for your generic confidence interval. We learned yesterday that's going to be B, which is your sample slope, plus or minus a T star for your critical value, times S. And so this is not S sub E, that's SE, because I want to distinguish, this is going to be S sub E right here. That's your standard sample standard deviation for your residuals divided by your sample standard deviation for your X all over the square root of n minus 1. And of course, one takeaway, I hope I made it clear enough yesterday, most of the time, this entire calculation is done for us by the computer, and we don't need to worry about all the different parts. All right, so what I want you guys to do at this point, because we started it yesterday, but we didn't have a chance to finish, fill in this equation with the actual values from this printout right here. See if you can remember exactly where to find those. Okay, so this is it. Now, I want to remind you what this printout, and I really hope today I do better than I did yesterday to make this a simple process. So you do not have to do much by way of calculation here, because unlike our previous confidence intervals, once you get to the standard error, it's already calculated for you every single time when you have the computer printout. All right, there might be an exception to what I just said, but generally speaking, the computer printout will have it. We don't care about the intercept, so this entire row right here, you can completely ignore. If it says constant or intercept, you can ignore it for inference. So this is representing, this line represents our slope, and the actual slope is found right here. Now this is a reminder, this is going back to what we did in Unit 3, because we saw computer printouts then. What we didn't look at before, but now we do have, is this is the standard error of the slope. And what this means is 0.2574 is that the sample gave us a slope that looks like this, but there's going to be this cone of possible slopes. All right, so this is just supposed to represent, here are all the possible slopes it could have, and the standard change away from the 0.77, so this is the B right there. But on average, the difference is 0.2574 in slope away. So if we consider these dashed lines to be the standard deviation, the standard error for where the possible slope could fall, then this would be, let's see, that's going to be about 1.02, something in that range. This is going to be about 0.52. Okay, so this true slope is going to be somewhere in that range if we're looking just one standard error away.
Wait, so that's like the B value for the slope, 0.52. Like the slope is 0.52.
Yeah, the slope would be 0.52. So in context, because this is saying how the change in age relates to a change in cholesterol level, then let's see, it's age and cholesterol level. For every year you are older, according to the sample, you might gain 0.77 points in cholesterol. But it could be for every year it's 1.02 or 0.52. But I want to remind you that this is just one standard error away. We're actually going plus or minus 1.96. So our true range is actually going to be, this would be our true confidence level, something like this. And it looks like a wide net that's being cast right now. But we're saying with 95% certainty, I know that the true slope is going to fall somewhere in this range right here. And we're talking about the slope only. We don't care about the intercept. Is this making sense? Okay. Now, every one of those is a positive slope, and it never gets down to a zero slope. A zero slope would mean there's no association at all. So it's going to be a positive slope. There is going to be an increase in cholesterol for every year that you are old. But we don't know exactly how much that changes. Okay, now the other number that's right here, this is the S sub E. So 46.16. In fact, the question right here asks you to interpret that. That is the standard, if it only tells you S, that's what it's referring to. The standard deviation, the sample standard deviation of your residuals. So now let me kind of create a new thing here. Let me just get rid of all this stuff. Okay, so now we're just looking at our sample data. So there was, a scattering around this from our sample. And this is actually 1,400 individuals. Right, so let's say it looked like this. I'm just putting a lot of dots. On average, any given residual, so this residual right here is going to be something, right? And this one right here is going to be some kind of residual. The average residual is 46.16. So if you were able to kind of synthesize this and come up with where the average difference is, then we would expect, even though it's predicted to be at some particular cholesterol level, the person might deviate by as much as 46 points away from that. So does that value make sense now? Okay, so this one is saying how the slope is going to change. And this one is saying how the residuals are going to change. All right, I'm going to pause there and see if there are any questions.
Wait, you said that both the S equals 46.16, those are two different things.
I just rewrote it. These two. S is S sub E. And S sub E is your sample standard deviation, sample standard error for residuals. And again, to get that, I would get the residual of every one of these points. So that residual, this residual right here, this residual, there's lots of data points. I get every single residual, put it into a distribution, and this would be my distribution of residuals. Some of them are positive residuals because it was an underestimate. Some of them are negative residuals because it was an overestimate. But the standard error is going to be that difference right there, which in this case is 46.16 away. Yeah. All right, now that's a lot of writing. So today we're looking at a linear regression t-test. So we're going to test hypotheses. Oh yeah, we can do that real quick. I'll also put Mr. Davis here. You don't need that. Okay. Oops. All right, so let's consider our null and alternative hypothesis for this hypothesis test. The null hypothesis always represents the no change option. So in this case, we're saying, or the no association option, maybe we can think of it this way. So our null hypothesis is always that there's going to be a zero slope between any two variables. And zero slope means there's no association. As one goes up, it has no effect on whether the other one goes up or down. And there we go. No relation between the two. And man, I just repeated myself, didn't I? The alternative hypothesis needs to be determined based on the context of the problem. Beta, which is the population slope, can be greater than 0, less than 0, or not equal to 0. So this, unlike our chi-square test where the hypotheses are always the same, this will change based on the context. But luckily, it's pretty straightforward. If we think there's a positive association and that as one goes up, the other goes up as well, then we say that our beta is going to be greater than 0. If we think that it's inverse, that as our explanatory variable goes up, the response goes down, then we would put less than 0. So in this case, a negative slope might be that we think there's a correlation between how much time people practice and their the time it takes for them to finish their 100-meter sprint or whatever, or a mile run. Let's go with that one. So the more time people train, the lower that number should be for their mile time. And there it is. All right. I don't know if you guys needed to see that anymore, but it's pretty straightforward. You're used to this type of stuff at this point. So we have the general formula and the specific formula for a test statistic when we're dealing with inference on linear regression. And you can see the statistic is B, the parameter is beta, and this is our standard error. But again, we typically don't even have to calculate that. Another nice thing about this, and this will come up, is that because our null hypothesis, because our null hypothesis is that beta is equal to 0 and that there's no association, that just gets canceled out to 0. So practically speaking, even though we still want to show the beta, practically speaking, our calculation is always just B over the standard error. So if that's helpful to think of it that way, we can find B from a printout. We can find the standard error from a printout. So as complicated as this looks, mathematically, we take one number from a printout, we divide another number on the printout, and we're done. And another thing to note is that this calculation is already done for us on the printout. So mathematically, this is about as easy as it gets. Okay. And there I went ahead and showed that. So that formula is given as such. So anyways, I'm gonna kind of, okay, this is one thing that's worth knowing, that you can use your calculator for linear regression t-test. In practice, you shouldn't need to, because you won't have to do that on the AP test, and you just kind of need to understand the concepts underlying a linear regression t-test and be able to use a computer printout to get your answers. So if you are doing a computer printout, you need to find the relevant numbers and plug those in. But like we'll see in a second, even those calculations are kind of done for you. You just need to plug the numbers in to show your work. The computer printout always shows a two-tailed test result. So if you need the p-value for a one-tailed test, just, well, say multiply it by half or divide by 2. So if that's something you want to make note of, then please do so. But I'll also pause here to see if there are any questions. I hope I'm not going through this too fast, but I want to pause periodically to make sure. Okay. Conditions for inference stay the same, no matter whether it's a confidence interval or a hypothesis test. We need to make sure that our scatter plot is linear and has equal variance, though sometimes we don't have the data display to show that. So in that case, we can assume that it does have equal variance if it doesn't give us anything else to work with. But if it gives you the residual plot, which will always look like this, with some dots scattering around a horizontal line, you can determine from there if it's appropriate to do the inference test. If it has unequal variance and it starts wide and gets really narrow, something like that, then you can make a comment to the effect, well, it doesn't have equal variance, so therefore inference is inappropriate for this problem. All right, the other one's independent, normal, and random. Independent, this is, if it's not independent, this is where you'd also use your 10%. So if you're sampling without replacement from a population, then you could also make sure it passes the 10% test. But independent is another way of talking about it. If they're independent events, you don't even need to worry about 10%. Okay, normal and random. The way we check normality is that normal probability plot where the hypothetical values on the vertical, so I'll just put HYP for hypothetical, compared to the real observations should match up into a line like that. And if it doesn't, then it's not normal. And what else? Random, that one's very straightforward. Okay, again, if there are questions on these and we're going through problems and you're not sure if we've met the conditions or why, then certainly please bring those questions to me. We can go through it together. Your degrees of freedom are still n minus 2. And now we can answer this question. Let's see how many practice problems. I gave us 3 practice problems here. And how about I'll just go through this first one with you guys. And this does give us a lot of information. This gives us, and I want to help you kind of read this. I'm not reading the prompt yet. You guys can kind of skim through that. But this is giving us our one variable statistic for profit and our one variable statistics for sales. So the average amount of profit is $209.84. The average in sales, or well, sorry, that's in millions of dollars, so more than that. But looks like the average in sales is 4,178.29 in millions. And you can see the variance right there and the standard deviation, which is the square root of those numbers. Those are one variable statistics. So we can use that for calculating things, but we don't need to. So let's kind of look at this. The question is there a significant association between sales and profits? Test an appropriate hypothesis. Our null hypothesis is that there is no association. The alternative hypothesis, does it tell us that there's an expectation one direction or the other for an association? All right. So I will say this. It doesn't specifically say, is there, maybe it would give you more to the prompt and say, a manager speculates that the higher the sales are, the higher the profits will be, which makes sense. But if it said that, then we'd be testing to make sure that this was a positive slope. As it's phrased, I'm not sure that it tells us which direction to check. So I'm just going to do this, that beta is not equal to 0. Okay. So jumping down, we could check our conditions for inference, but maybe we'll just kind of briefly talk about it. I don't want to dwell on this too much because chances are it's going to be a question specifically about conditions for inference if you need to worry about it. And if it's a question asking you something like this, they're not going to expect you to check conditions also. They're going to say, assume all conditions for inference have been met. And it says right here, the assumptions for regression inference appear to have been satisfied. So at this point, I'm just going to put a big check mark beside it. Okay. So now let's kind of look at the next part. My generic formula for a test statistic is stat minus the parameter divided by the standard error. In this case, my test statistic is going to be a t statistic. The stat is b, the parameter is beta, the standard error is s sub e all over s sub x times the square root of n minus 1. And luckily, you do not need to have that memorized. You just need to copy it down from this so that you're letting the grader know, I know what formula is used here, even though I'm not specifically going to be using it. I'm letting the calculator, the computer, do the work for me.
I know that beta is 0, but what does beta represent?
Beta is just the population slope. So because we're drawing an inference on what the true population slope is going to be. Yes. Yeah. And we're testing to make sure that there is an association. And if there's not an or if there is an association, it would have to be significantly deviating from 0. The slope would. Does that make sense? Yeah. Okay. So I'm going to erase this so we can look at this printout a little better. The intercept we can completely ignore because we don't do any inference on intercept. So what I'm going to do now is I'm going to calculate my t. And right here, the first number, almost always, though there could be exceptions to this, the first number is going to be your slope, your sample slope. So that's going to be 0.092498. Why not? I'll just write the whole thing out. Then we can see this is our standard error for our variable of interest. So that's already calculated. That's 0.0075. Okay. So if we look at this, we can, well, that's straightforward. Sometimes it even gives you the next couple of calculations already done, but I'll just plug this in. 0.092498 divided by 0.0075 gives me a t statistic of 12.333. And we all know that's a huge test statistic. If we want to get our actual p-value, we can use TCDF. So I want to go from 12.333 to positive infinity. Vera, what's the probability of getting an outcome that extreme or more so? So I'll kind of do this in the corner. TCDF going from 12.333 to positive infinity. And then it also asks for your degrees of freedom. And that's it. So my degrees of freedom here, how many? Okay, there are 79. So there's going to be 77 degrees of freedom when I subtract 2 away from it. So there we go. 12.333, 99, and 77 degrees of freedom. This is so incredibly small. So I just plug that in my calculator. I know I kind of just did all this work, but I wanted to run through this first one. So I got something to the negative 20th. So you can report that, or you could just say, yeah, that's less than 0.05. Okay, you can write the number out. It's not a bad idea to do it. We, just to quickly wrap this up, yes, we reject this null hypothesis because our test statistic was less than the p-value. There is convincing evidence that sorry, I was jumping ahead. There's convincing evidence that there is a significant association between sales and profits. All right. And the other thing I wanted to mention, and I kind of skimmed over this number that we got for our p-value, maybe you were thinking this, technically we need to double it. It's so small that doesn't matter, but we're doing a two-tailed test. So if you want to report the accurate one, you just take that times 2, and you can get your 6.5 times 10 to the negative 20th. Does that matter practically speaking? No, but if it's a multiple choice question and they give you the actual options for your p-value, then you want to make sure that you are keeping that in mind. Okay. So now there's another question. Do you think, actually, well, I'm sorry, pausing again, see if there are any questions on that process we did. So as bad as this might have started out, does this seem like it's pretty simple mathematically? Okay. All right. So let's now answer the next part. Do you think that a company's sales serves as a useful predictor of its profits? Use values of both R squared and S in your explanation. All right. Well, I want to see if you guys have any thoughts on this. You can think about that for a few minutes or a minute or so. The coefficient of determination R squared says what percent of the variation in our response variable is explained by the variation in our explanatory variable. So, and this is where, if you remember, I encouraged you guys to actually draw a quick scatter plot. And it looks like we are predicting profits from sales. So sales are going to be right here, and profit is right here. This is a 0.092 slope, so it's not that big, but it is pretty high correlation between it. And the question is this a good predictor? Is this model a good predictor? So here's what I would say. I actually haven't looked up the official answer. But I will say this, because it asks us to also use S in our answer. And we talked about that one just a second ago, but we'll come back to it. We can say that 66.2% of the variation in profit is explained by the variation in sales, or is explained by the model. However, S is 466.2. So if we interpret the slope real quick, we're saying that for every additional $1 million in sales, so for every, I just want to kind of write this out, for every additional $1 million in sales, we would expect, what does our slope say? 0.092. So I'll even put that in, that's going to be $92,000, 498 in profit. So that is good to know. You sell $1 million more, you make $100,000 extra in profit. But here's the problem with this. Our S is 466.2. So the residuals, the average residual is 466 million. Okay. So look at this, 466.2. So even though I've not drawn this very well, but let's imagine I have some dots out here so I can just draw it a little better. The average difference, if I had the average one right here, that would be $466.2 million off of what was predicted. So yes, an extra million gets you $92,498, and it has a pretty high R squared, but the difference from what the average difference from what would be predicted is almost $500 million, if I'm reading this right. So is it that useful? Not really. Not really. But I want to see if I'm far afield from what they say the answer is. We can find out if they have a better answer for this. See, the textbook can be good. What is this problem number 30? Okay, it says somewhat. Okay, so here's from the textbook. Sales accounts for 66% of the variability in profits. Although S is nearly $500,000, the mean profit for these companies is over $200 million. So that doesn't give me a great answer. So, but bottom line is whatever relationship we're finding is dwarfed by the average difference. So that number is huge. Does that make sense? Okay. I hope that makes sense to you guys. I'm going to pretend it makes sense to me. All right. So with this one, I'm going to do this first of all. I'm just going to give you your specific formula for this problem, which is T equals B minus beta over S sub E divided by S sub X, and the square root of N minus 1. And I'll just put this equal right here. You guys can go through and you can plug in the correct information so that you can calculate the test statistic. Okay, we got the correct numbers plugged in. You can do that math really quickly on your calculator and find out what our T score is. All right, so we've got 1.118. I didn't do that math myself, so you guys can make sure that you agree with that. And at this point, you want to figure out what is the p-value of this. So it doesn't give that to you. How can you find the p-value? TCDF. There it is. Go ahead and give that a shot. Plug in everything correctly, and I'll just put P equals right here, p-value equals 0.139. Assuming our alpha level is 0.05 as usual. Do we reject or fail to reject the null hypothesis?
Fail.
We fail to reject the null hypothesis. There is not, because our p-value is greater than our significance level, we fail to reject it. There is not convincing evidence of an association between brain size and IQ. There you go. All right, state your conclusion about the strength of this association. If they're talking about correlation right here, this is a good review thing more than specifically regression inference. But remember, if your R squared is 6.5, we can do the square root of 0.065. That'll give us our correlation coefficient, which is what we consider the strength of it. And I get 0.255. The one thing, and this is good for review, you need to remember when you take the square root of your R squared, it could be a positive or a negative correlation. In this case, it looks to be positive, but double check, and sometimes it gives you this question without the aid of a table or of a scatter plot. So you kind of need to think of what your variables are, and do they seem like they're directly or inversely related, positively or negatively correlated with each other. So in this case, we could say there's a 0.255 correlation between these two variables, which is considered a weaker positive correlation. Okay. And the last one here, this is something I wanted to point out to you. In fact, we don't even need to go through this. Let me first of all clear all drawings. it gives us all this stuff right here, but look at what is wonderful about this. It gives us our coefficient, it gives us our standard error. There's not even really enough information to work with this, but it even gives us our, when you have the next one over, this is your test statistic. There's a negative 5.95 test statistic right here, and the p-value is less than 1/10,000. Keep in mind that's a two-tailed test, but we are, you know, that's really, really small. So it doesn't really matter. The fact that it's two-tailed, we could divide it by 2 to get our one-tailed test, if that matters. So when they give you this full printout, and with the last couple, they only give us these two. But if they give you the entire range, all the columns, then your work is done for you completely. Okay, so you guys, does that make sense what that negative 5.95 is? Okay, and of course the p-value. So now you can state your hypotheses. The one thing we didn't, and this is me working fast and not thinking through everything, the last time we didn't set up our hypotheses, so we needed to remember if it was supposed to be a one or a two-tailed test. We got 0.139. If it was a two-tailed test, we'd have to double that to basically 0.28. So either way, we reject the null hypothesis. And I don't believe it said we're testing a one-way test. So we would have technically wanted to double that last p-value. If this is a two-tailed test, it's already giving us a two-tailed. Okay, it does give us the residuals. We can determine if this looks to be linear or nonlinear. So maybe this is some good review. Looking at your residuals and the original scatter plot, does this appear to be linear in form?
I don't know.
Yeah, it's looks a little bit like America.
Oh wait. I guess that. Yeah. I got confused. I forgot the volume plot.
Yeah. So in this particular case, they're doing a weird thing right here where they are comparing the predicted to the residuals rather than the MSRP. So it's getting thrown off a little bit, but we can still see if it's a linear or nonlinear in form. So anyways, we've got, it appears to be almost nonlinear. So maybe we could determine here that that is technically not appropriate to use because it appears to be nonlinear. And you can see that we have very few residuals down to the low end over here and a lot more right here, but then we get a lot more right there up at the high end. So you could argue this is nonlinear and therefore we shouldn't even do a linear inference. All right. So I'm throwing out a lot of things to consider as you're going through this. And hopefully I'm not doing it in a way that's confusing you. But again, a good option for this, what I always encourage you to do is, oh, I need to make sure this is opened up for you. You've got your, now your test is not on Friday. I'm sorry, your test is on Monday. But your AP Unit 9 progress checks will be opened up today. And you can see what kind of questions to expect. These 5 questions are good for you to run through. Make sure you understand the process. And remember, I always give you questions have the answer key at the back. So if you're getting the answer and you're able to double check and see if you got it right or wrong, anything in there, just, you know, work with that. Don't worry about any problems where I ask you to put in a list and basically do the test by hand because you won't need to do that. So with that, if there are questions on things we've gone over today, certainly stick around. If there's questions on anything else, stick around. If you feel like you're good to go to try this out on your own, have a wonderful day, and I will see you guys tomorrow.